In the not too distant future, you're going to be working on the problems in the text over section 6.2. So I wanted to show you something similar to problems 1 and 2 here, because those are straight up applications of this big theorem that we just talked about in the last slide. So I am going to give you a typical problem where you are asked to determine the minimum radius of convergence for a series solution to the given differential equation about the specific ordinary point that you're given in the problem. So here's a differential equation, and it's a nice cute little guy. The ordinary point that's specified here is x sub 0 equal to 1. So you're looking for this minimum radius of convergence, and the big theorem tells you that minimum radius of convergence is the radius of convergence is bigger than or equal to the distance between the target point and the nearest singularity. So to solve this problem, what you need to do is you need to find what the singularities are. So to find who's the singularity, you go to your differential equation, and first thing is you want to make sure that you're in standard form. So standard form means I'll divide through by that front coefficient there on the y double prime. When in doubt, you can get partial credit by putting your equation in standard form. So this would be y double prime minus 3x over x plus 1 y prime plus 2 over x plus 1 y equals 0. So your p of x function here is minus 3x over x plus 1, and your q of x is 2 over x plus 1. And these guys are going to have series solutions as long as they're defined. The only place where you have trouble is if you have a zero denominator, which is when x equals minus 1. So that's your singular point. Happens to be only 1 in this particular example. So the ordinary point was 1. The distance between it and the singular point is 2. So that means your minimum radius of convergence is 2 units. Yay! Problem 1, done. Let's do another. Why stop at 1 when you can do 2? So let's take this creature. Let me find my creature. Here's my creature. Let's take x squared plus 9 y double prime plus xy prime plus x squared y. And let's figure out what the minimum radius of convergence would be if I were to expand about the ordinary point x sub 0 equals 0. Okay, so we're looking for the minimum radius of convergence here. Same method as before. In order to figure out what that minimum radius of convergence is, we need to figure out the distance between the target point and the nearest singularity. So you need to find your singularities. To find your singularities, you need to be in standard form. Alrighty then. So as in the last example, everything is good and happy unless you have a zero denominator there. And yes, you can actually double check from this that you will have an ordinary point at 0 here because the function's defined at both of these functions are defined when you put in target value of 0. So what are the singularities? The singularities are going to be where the denominator equals 0. So those are your singular points. So you have 2 complex singular points. But what you need to look at is how far away are, how far apart are these points? So you look at that and you say, well, wait a minute, that's 3i and that's 0. How do I know how far apart they are? Here's how you know. Here's your origin, 0, 0. And here we have 0 plus 3i. So you're writing, actually, you're taking this as 0 plus 0i is the way that you're looking at it. And you're looking at these as complex numbers. So if x equals plus or minus 3i, then it lives at 1, 2, 3i and 1, 2, minus 3i. And the distance away from the origin in either case is 3 units. So here your minimum radius of convergence is 3. So now we're going to take that same equation that we just used, and we're going to determine the minimum radius of convergence for it in terms of powers of x minus 4, not 0.4, that's a scribble. So this means that the target value is 4. We already put it into standard form in the last example. And we already know our singular points are plus or minus 3i. So again, now you're working in the complex plane. Here's my point. 4 plus 0i is right here. My two singularities are 3i and minus 3i. And then to figure out the distance between this point right here and either one of the singularities, you'll just use the Pythagorean theorem, which is also known as the distance formula. So to get this distance, you'll take the long way around. You'll take the fact that that forms a right triangle. And this right triangle here, which would give you the distance between the target point and the other singularity, they're symmetric, so we only have to do this one time. If you compute your distance there, this is 4 units, this is 3 units. So that means the pink distance here will be, so the distance between 3i and 4 will be the square root of 3 squared plus 4 squared, which is better known as the square root of 25, which is better known as 5. So your minimum radius of convergence here will be 5. Oh wait, he should be wearing a face mask.